Welcome to another presentation regarding trig functions and odd and even functions. So this is often covered in this course in something called trig preliminaries. So I'm going to go back and have a look at some of this trigonometry and see what's going on. Well, that raises the question, can you see what's going on around the screen here? And I guess you can see the reciprocal functions. Cosec t is 1 on sine t, sec t is 1 on cos. We've seen a bit of this before, and cot or cotangent of t is 1 on tan. So we're going to have a very brief look at these functions and why we might be interested in them. And I think you can see they're going to have some problems from these denominators, because they're not going to be everywhere defined for all t, are they? Because you can't divide by 0, so that might be a starting point or a point of interest to get started with these functions. And then down the bottom, odd and even functions, that's got something to do with these diagrams here. And so can you see what's going on? Well, sort of. This one's got symmetry here about the y-axis, and this has got point symmetry across here about the origin, isn't it? That bit and that bit sort of match up. And diagonal or point symmetry there. So let's have a look at these particular functions, these groups of functions, and see if we can get a better understanding of them. So come down, let's have a look at odd and even functions for a start. And functions that are symmetrical about the y-axis are called even functions. So the y-axis acts like a mirror here for symmetry, and we've got functions which, when you plot y as f of x, then or plot f of neg x, you get a perfectly symmetrical function. F of neg x comes out to be a symmetrical situation. So symmetry about the x-axis is where functions for the neg x value, when you plot it in there, gives you the same set of values. So these are even functions, where you've got f of x values exactly equaling the neg or f of neg x values. This side is identical to this side, if you like. So that's what we're going to try and look at. And can we tell from the formula for the function whether they're going to have nice symmetry about the y-axis? Let's have a look. So here's our definition. A function is said to be even, and therefore its graph is symmetrical about the y-axis, if when you sub neg x, the values over on to the left of the origin, into the function, you'll get the same set of f values as if you subbed in positive x. So that's our definition. So let's have a look at what we do to indicate that or to prove that. So these screen clippings now are from Hayes and Harris publications. So you should have that book. Let's have a look at showing that this function is an even function. We already know it is, because the graph of f of x equals x squared is symmetrical about the y-axis. So we'd be expecting our little algebra test to come up positive here, because the positive x values give the same function values as the negative x values. Symmetry there. So how do we go about it? Well, first thing we do is look at neg x subbed into the function, and we're going to put that in carefully. So it was x squared, so now it's neg x squared. And because it's all squared, negative times a negative is a positive, so it's x squared. Therefore, what do we notice? When we put in the neg x side of things, you get exactly the same as the function value originally for all x, and we should put that. Therefore, this is an even function, because putting neg x in, you have just proven without actual values, so it is a deductive proof that you're getting the same set of values. Let's do cos x. So what do you start with? Sub in neg x into your function. Here it is here, do it carefully. And then the cos of neg x is equal to the cos of x. Right, so that's a property of cos. Excuse me, property of cosine. And that gives you then the function back again for all x. We're not using particular values here, so we're proving it for all values of x. And then your comment, f of x is an even function. So because these are little proofs or show that's, it's very, very important that you set out the steps according to the definition. Let's take this one. Here's our function. Substitute neg x carefully in each spot. So instead of x squared, it's neg x squared. Instead of cos x, it's cos neg x. Neg x all squared is plus x squared. Cos of neg x is the same as cos of x. Property of cosine. There. What are we saying? Cosine is positive in both of those quadrants, S, A, T, C if you like, because the cosine is the x coordinate there of points. So in those two quadrants, the x value is going to be positive for all points. So therefore, we end up with a function exactly equal to the starting values, even though we've subbed in neg x's. So therefore, f of x is an even function. So these steps, this procedure is important to establish a show that or a proof of evenness for that function. All right, your turn. So let's have a look at the other one now, the odd functions, and that is when you plot the function, there it is, from the positive side, you get similar values, but these are negatives. Okay, so in other words, when you sub in neg x, you get this set of values, only they're all negative, minus f of x. And this is called oddness, or it's point symmetry about the origin, so that when you sub in your neg x on that side, they give the negative values of the positive side. So you've got this sort of symmetry across here. And x cubed is a good example of that. As I say, remember the graph of x cubed? So here we go, we're going like this, that should go through there. Hard to draw on the screen. So here that's x cubed, and all these values become these, they're all multiplied by neg 1. So the positive set minus times the negative set. Because the negative set here are negative, times the negative, you'll get this group up here. So there it is, there's the definition. This time we're going to sub in neg x into the function and show that you get negative the positive values that you would sub in. Okay, let's have a look at an example or two here. All right, so if that's our function, x cubed, I just said that that was odd. So how do you prove it? Sub neg x into x in the function. So it becomes neg x all cubed, neg raised to the 3, negative times negative is a positive, times another negative is a negative, x cubed. And so that is, that negative out the front says our function for negative x is minus the function value for x. And we're not assuming any x, so we're going to say it's for all x. Therefore, this original function is an odd function because you've got a negative outside of the usual function values when you stick in a positive. So let's do x to the 5th take sine 2x. First of all, sub neg x in place, oops, no, we're up here, f of x equals sine x. Sub neg x into where x is, so it's sine neg x. And sine of neg x is minus the sine of x, property of sine. Just remember, that's a little bit different from the cos one. So here, if that's your positive angle, here's your negative angle down here. The sine is the y value. So this will be positive, this will be negative. And similarly, as you go around the circle. So the sine of neg x is minus the sine of x, property of this circular function definition there. So we therefore say when you subbed in neg x, you got values which were the negative of the positive values there, or the values of the function when x was subbed in as a positive. So therefore, f of x equals sine x is an odd function there. All right, what about the last one? X to the 5th, take sine 2x. Usual procedure, sub in neg x in place of x. neg x to the fifth, sub n neg x there, minus sign 2 times neg x, and a negative raised to an odd power is negative. So it's neg x to the fifth, and sine 2 times neg x is minus sign of neg 2x. And then we can say properties of sine. Sine of a negative angle is minus the sine of the angle. Property of sine. And that's negative times a negative is a positive. So we now have from this function generated this one, which is, it's negative, isn't it? Multiplying that original function by neg 1, you would get this. So we've established that f of neg x is minus or negative f of x. So it's an odd function, even without graphing it. We're trying to tell people about whether these sorts of symmetries exist without a calculator, without drawing a graph. All right, now it's your turn to try and look at some functions here. Show that the following functions are even or odd, and I think you should do all of these and go through the processes there and see what you think. Okay, let's go down and have a look at the answers now. Okay, question 1. Make sure the setting out is complete, showing careful substitution of neg x. And question 2. I think this was omitted from the original question. Let's go back up and just change that. Yep, it was chopped off there. Okay, so just check that. All right, let's go on now. The question 2. And then finally question 3. Okay, what's the setting out? The setting out is crucial. You must show the careful substitution of neg x in place of x. All right, let's move on. What else can we do with this? Well, here's an interesting little proof. Prove that the sum of two odd functions is also an odd function. So here we are. Let big F of x be the sum of little f of x and g of x, and where those two are both odd functions. So same process. Stick in neg x in place of x everywhere in the original function. Okay, so we've got this line. Now if these are odd, f of neg x is the negative of f of x, and g of neg x is the negative of g of x. We can factor out the negative, f of x plus g of x, which of course f of x plus g of x is the original function. So we've actually shown what's required, that our big sum function, big F of x, equals minus f of neg x. Okay, so therefore the sum of two odd functions is also odd. So we do a few things like that, carefully sticking to, showing a careful substitution here of neg x into f, and that it's going to be equal to the negative of f of x in the odd case. All right, here you go. Prove these. Again, the sum of two functions, you'll let big f of x equals f of x plus g of x, and go through a general deductive proof. No particular numbers or functions. All right, pause it and have a go. I'll show you the solutions now. So question 4, A, B and C. And 5, A, B and C. Right, some little proofs there. That's a little bit harder, those last little bits there. All right, so that's all we're going to do on odd and even functions. I think you get the idea. What we now want to do is look at these reciprocal trig functions and have a look at what their graphs might look like. So we define them as, the reciprocal is 1 over. So secant of t is 1 over the cosine of t. The cosecant of t is 1 over the sine of t. And the cotangent of t is 1 over tan, which you could put as cos over sine. So I'll just write this down, that sec means the secant, cosec, the cosecant, and cot, the cotangent for the reciprocal functions. Okay, so what are we expecting to be the challenging nature of these things? Well, it's going to be, this function is going to be undefined for cos t equals 0. That implies when t equals pi on 2, 3 pi on 2, etc. Or pi on 2 plus k pi, if you like. Okay, 2 points in one revolution at which cos is 0. Yep. And that's going to be a point at which they're undefined. So we can do each of these here. When is tan undefined? When one on tan is undefined when tan is 0. When is tan 0? When the sine is 0. So putting these equal to 0 is going to make these functions be undefined and have asymptotes. So let's go down and have a look at some problems here, and want you to investigate exactly that. What does technology say to you about each of these functions? And then, of course, just getting used to working in here, cosec, 1 on sine, cot, 1 on tan, 1 on cosec, 1 on sine. So just getting used to the algebra. If you're dividing by a fraction, as this is, you'll invert and multiply. So replace each of them with their definition. Sec is 1 on cos. Okay, and try and simplify. Okay, pause it and have a go. I'll show you the solutions in a minute. Coming down to 5 is a practical problem. Show that AC, what's the maximum length you can get around that corner, if you like. Or it could be a passageway in a house and a ladder you're trying to move around, something like that. There are a few problems like this. And you can look at what you're asked to show, that AC has that length, and split it into 2 parts. Sorry about that. Put it into 2 parts here. The first part is AB. Try and get that, plus BC. All right, see what you can do with those. All right, now more simplifications here. Okay, and using your prior knowledge of some of the identities. 1 plus tan squared equals sec squared. We've seen that before. And then to show that here. So just taking one side here, we'll probably take this side, left-hand side, and play with it and see if we can get it to 2 cot theta with a common denominator and so on. So setting out with show that's are very important. To take the left-hand side and to work carefully, simplifying it, and hopefully to come to the right-hand side. Or if it doesn't, start on the right-hand side and see if you can get a common expression so that you get equality that way. All right, you ready to see some answers there? So I'll just go through the pictures. Okay, the graphs. So you can see, as I said, the first one, sec, which is 1 on cos, has got problems at pi on 2 and 3 pi on 2 because cos is 0 there. So you're going to have an asymptotic approach. So these are interesting functions, and they should be this U-shape sort of thing in there. Not really a parabola, a little broader than that in a sense. All right, have a look on your calculator and make sure you adjust the view window so you get a good size of that presentation, and you can study the asymptotic behaviour. So just check here, 1 on tan. When is tan undefined? All right, when is tan 0? When sine is 0. So all these points here are values of t, where the sine of t is 0, and just remembering that 1 on tan, okay, will mean it's cos on sine. That's going to be undefined if the bottom line is 0. Okay, now that's at 0, pi, and so on. All right, mark your work there, particularly the simplification ones coming up. Question 3, C and D, E and F, and almost G and H. There's G and H. And question 4. Okay, question 5, a sort of practical problem. 5 there, splitting it into 2, AB and BC, and adding them up, making these little right angle triangles with that theta there. Okay, that will be a common angle in both of them with those, with the triangles we've got there, because AX is parallel to BY, which is along the x-axis, if you like, sharing that direction. Okay, 6, A and B, let's come down, see if we can get C on there. Not quite, we'll do that in a minute. Excuse me, and C now there, bit of work. And the last one now is question 7, and there's A and B. All right, and then C, and that's it for those. So there's a lot of skills here that you need to get on top of. Fairly simple ideas, concepts aren't too hard. That's all for me from this little section. I'll catch you a bit later. Cheers for now.